Hello everyone, I am Siddharth. I am an alumnus from IISER TVM, and today we will be solving a question that appeared in the IISER entrance exam in the year 2018. This question talks about two simple pendulums of length 1 meter each and whose bobs have mass 1 kg and 2 kgs. Now right off the bat we can see that even though both the bobs have different masses, this actually has no effect on the time period of a pendulum, which is given by t is equal to 2 pi under root length upon effective gravity. Now why I am writing effective gravity? Because in the question it goes on to say that though pendulums are kept in an elevator and it starts moving vertically downwards with acceleration g by 10. So if an elevator starts moving vertically downwards with acceleration a, everything inside the elevator, if we consider in the elevator frame, will experience a pseudo force that will be given by opposite to the acceleration a. So we can write the effective gravity inside the pendulum as g effective is equal to g minus a, and since acceleration is g by 10, the effective gravity becomes 9 by 10 times g. So we can just substitute this value in the formula. Since the length is 1 meter each, the time period just becomes 2 pi under root 1 meter upon effective gravity is 9.9 by 10 g. You can write 9 and 10, sorry, g over here. If we calculate, the value of 10 is approximately g itself, so we can cancel, and square root of 9 becomes 3, so we are left with approximately 2 pi by 3. So the time period will be just a little bit greater than 1. We can say so 2.1 second. So B is the correct answer in this case. This question says that the potential energy of a point mass is given by this function. If it starts from rest at this point, then we need to find the maximum speed that it will attain during the entirety of its motion. Now from the initial position of the object, we can substitute this x into the equation for its potential energy to get the initial value of its potential energy. And since the object had started from rest, this will also be the total energy of the object initially, and since energy is conserved, we know that throughout the entirety of its motion, the energy of the object should be equal to the initial potential energy. So if we substitute the value of x into the potential energy function, we get initial potential energy is equal to A into A upon B, that is x, plus B into A upon B, which gives us twice of A square upon B. So we need to ensure that the energy of the particle during the entirety is equal to this value of initial energy. Now since we need to find its maximum speed, we are concerned with the maximum kinetic energy that the object will attain, and we know that when the kinetic energy of the object is maximum, its potential energy will be minimum. So let's minimize this potential energy. We can minimize it by simply taking the first derivative of its potential, that's given by A plus 2 into Bx, and setting it to 0. Now solving this equation, we get the value of x where the potential energy becomes minimum will be equal to simply minus of A upon 2b, and at this point the minimum value of potential energy V minimum will be equal to, we can just substitute this value into the expression, A times minus A by 2b plus B times A square upon 4b square, since we are squaring these terms. This term gives us minus A square upon 2b, this term gives us A square upon 4b, so we will be left with minus A square upon 4b as the minimum value of the potential energy of this particle. Now finally we can just conserve the energy at this point. If potential energy is minimum, kinetic energy should be maximum, so we can write half into mass of the object into maximum speed attained by the object plus this value of minimum potential energy, that's equal to minus of A square upon 4b, and this is the total energy of the object which is conserved, so this should be equal to twice of A square upon 4b, twice of a square upon b, sorry, not 4b, just a square upon b. Rearrange the terms, we get twice of a square upon b plus a square upon 4b. That will be added, and we can thus find the value of its maximum speed. And so if we solve this equation for the value of v, we get it as v max is equal to 3 on top into a upon under root 2bm. Thus option A is correct in this question. So you have been given a triangular wedge which is an isosceles triangle because both the angles at the base are equal, and there is a pulley at the apex which has a string passing over it connected to two masses, and there is friction everywhere in the system. All the values are given symbolically. Now when you've been given a symbolic question like this where not even a single number is present, the first thing to understand is you are in for a long derivation. Be prepared to write a lot of steps, write clearly, and don't miss out on any calculation step, because if you do, you might end up making a very critical mistake at that point which will ruin your entire answer. So let us just first write down everything that this system can tell us. We have been asked the ratio m1 upon m2 such that the whole system is in equilibrium, which is good because that just means we have to balance forces on each and every object in the question, and we'll be done for. So let us first draw the forces that are acting on the two blocks. Of course, their individual weights will be acting vertically downwards. Here's m2g and here's m1 into g. And since there is a wedge, it will exert normal reaction forces on both of them. Let's call this force as N2 and let's call this force as N1. Now we've been given that the mass M1 is greater than the mass M2. So M1 will move in the downwards direction and M2 will move in the upwards direction, which means M1 will experience a frictional force opposite to its motion, that is upwards along the incline. Let's call this force as friction force 1, and M2 will experience a frictional force downwards along the incline F2. Of course, there will be tension in the string which will be common for both the objects. So now that we have the force diagrams for both the objects, we can start with balancing them. Now we'll balance the forces in the perpendicular direction to the incline and the horizontal direction to the incline, because that is much easier since we have only one force to resolve. We know that the normal reaction force balances the cos component of the weight. So let us write down the values of N1 and N2 both. N1 will be equal to M1 into G cos theta, and N2 will be equal to M2 into G cos theta. Since it's an isosceles triangle, theta is equal for both the objects. Now let us get to balancing the forces along the incline direction. For the first object, it will experience the sine component of its weight downwards along the incline, which will be balanced by the tension force as well as the friction force. And we know the value of friction force in limiting case is equal to mu1 into N1. Since we know the value of N1, we can just substitute over here. Expanding all of this, we get M1 into G sine theta should be balanced by the tension plus mu1 into normal direction force, that is M1 into G cos theta. Similarly, balancing forces on M2, we get M2 into G sine theta should be balanced by the tension, and this time since the friction force is acting downwards, we will minus M2 into M2G cos theta. Now we don't know the value of tension, and that is not even relevant to what quantity we are trying to calculate. So we need to first eliminate T from both of these equations. Let's call this equation 1, let's call this equation 2, and we can see that if we just simply subtract 2 from equation 1, T will get cancelled from both the sides. So let's just write down that expression. M1G sin theta minus M2G sin theta will be left. Let's write down here M1 into G into sin theta minus M2 into g to sine theta. T will get cancelled and what will be left is the friction forces on both the objects, m1g cos theta plus mu2 into m2 into g cos theta. So this is the equation that we are left with after subtracting equation 2 from equation 1. Now since we require the ratio m1 upon m2, we need to get this quantity in our equation, which can be achieved simply by dividing the entire equation by m2. Let's divide m2 in all the terms. Now in terms where there is only m2 present, it will get cancelled happily, and in terms where there is m1 present, we will end up with the ratio that we have. Now if we simply rearrange these terms so that all the terms containing m1 and m2 are in the LHS and all the terms containing only sine theta and g are in the RHS, we will be left with m1 upon m2 should be multiplied by g sine theta minus of mu1 g cos theta, g sine theta minus mu1 into g cos theta. This will be equal to, we have mu2 into g cos theta in this case, mu2 into g cos theta, and we will add g sine theta to it. So simply we will divide this bracket on the RHS and will be end up with m1 upon m2 is equal to mu2 into g cos theta plus g sine theta upon g sine theta minus mu1 g cos theta. Cancelling g from all the sides, we can see that option C is the correct answer to this question. This question talks about a particle of mass m1 moving with an initial velocity of vi. It is said to have collided with a stationary particle of mass m2, and the question goes on to say that after collision, the velocity of both the particles becomes vf. So obviously this is a perfectly inelastic collision, and we know that in a perfectly inelastic collision only momentum conservation is enough to find the final velocity. So let's apply that. Initial momentum is m1 into vi because m1 was the only particle in motion, and finally both the particles will move together, hence the final momentum of the system becomes m1 into vf plus m2 into vf. We can take vf common, and from here we can find that vf equal to m1 into vi upon m1 plus m2. We need to find the energy lost in the collision, which is simply the difference in kinetic energies initially as well as finally. So let's just write it down. The energy loss is equal to half into m1 vi square minus half into m1 plus m2 because they both moved as a combined mass into vf square. We can substitute the value of vf over here as m1 vi, m1 into vi upon m1 plus m2 whole square. m1 plus m2 gets cancelled from here, and in order to make the denominators equal, we can multiply and divide the first term by m1 plus m2. So we'll get in the numerator m1 square plus m1 m2 upon m1 plus m2 into vi square, and we'll subtract m1 square vi square upon m1 plus m2, of course half into vi square. And we can see that after cancelling and taking the terms together, we get option B as the correct answer. Now this question says that an object of mass 100 grams slides from a height of 5 meters and then enters a flat surface which has a coefficient of friction of 0.5, and we are asked what will be the work done by the kinetic friction. Now we know that conservation of energy holds for the entire duration of its motion. Since the object starts from rest at the highest point, it has a potential energy of mgh at this point. When the object reaches at the bottom of the track, we can take this as a reference point that gravitational potential energy is 0 at this point. So the object will only have kinetic energy given by half into m into v square if it has a velocity of v at this point. since we conserve the energy, this kinetic energy will equal to the potential energy with which the object had initially started with, and the kinetic energy at this point will remain with it as it starts to slide on the flat surface. And since the object comes to rest at the end of it, the work done by friction we can write as mu into mg into x. This work done by friction will completely balance the kinetic energy with which the object had started sliding on the track, and we know that this kinetic energy was equal to mgh. So we can directly equate this work done to mgh, and we can get from this equation mg cancels with mg, x becomes h by mu, and since we know mu is half, x will be twice of h, that is 10 meters is the answer to this question. So we can clearly see that when the motion is divided into many such segments and the object is coming to rest at the end of the motion, all you need to do is equate the work done by whatever force is bringing the object to a halt. In this case it's friction. You can have spring force, gravitational force or any other force. The work done by that stopping force will be equal to the initial energy that the object has started with, and it doesn't matter what kind of complicated motion the object might go through. All we need to do is simply equate the initial energy and the work done by stopping force, and we can get the answer. Thank you for watching this video and subscribe to our channel for more such content.